Energy 1.2 says that you need to explain conservation of energy using kinetic and potential energy equations for situations involving energy transfer and transformations. So the main focus on the conservation of energy is this equation here. The first part of it, you can see they call the total mechanical energy, or the mechanical energy initial, and the mechanical energy initial equals the mechanical energy final, meaning that the initial gravitational potential energy plus the initial kinetic energy, like whatever you start with in these two types of energy, is equal to the gravitational potential energy final and the kinetic energy final. So essentially, we know that the conservation of energy means that energy is neither created nor destroyed, it simply changes forms. And if we're talking about a complete transfer in terms of gravitational potential and kinetic, whatever we start with initially is what we're going to end with at the end of whatever the scenario is that we're talking about. So I'm going to run you through an example of this so that you can kind of see what it looks like. So classic example, let's say we just have a bookshelf and we have a ball resting on the top of this bookshelf. Well, let's say the bookshelf is 2 meters and the ball is 5 kilograms. So if I want to first figure out what the initial energy is in this scenario, I'm going to be looking at EG initial plus EK initial. Well, at the top of this bookshelf, this ball has only gravitational potential energy. This ball isn't moving, therefore there's no energy due to motion, so I'm really only looking for one thing. And you can see that if I'm given the mass and I'm given the height, there's really only one thing that we can calculate here. So we're going to find the gravitational potential energy, and we know that that's mass times gravity times height. Well, we know that the mass is 5 kilograms. We know that gravity is 9.8 meters per second squared. And we know that the height in this particular case is 2 meters. So we're looking at 5 times 9.8 times 2. So if we just did 5 times 2, we would get 10 times 9.8 is going to give me 98 joules of gravitational potential energy. So in this particular equation, the initial gravitational potential energy is 98 joules plus the initial kinetic energy we determined was 0 joules. So the total mechanical energy at the start is just 98 joules. Okay, so that's pretty simple. We know what we have to solve for. We're only given a limited amount of information. So we do know the information or the energy that we've actually started with. Okay, so we have 98 joules of gravitational potential energy at the top. Again, 0 joules of kinetic energy at the bottom. And then we need to figure out final. So let's say in this scenario, the ball rolls off the ledge. And we're going to look at the ball on its way down from the fall as close to the ground as possible, but without touching. So what I'm getting after here is that the ball is falling, it's in motion, so we're talking about kinetic energy. However, the ball is so close to the ground that it has no gravitational potential energy. So now we're going to be looking at the final scenario, EG final plus EK final. In this particular case, whatever the gravitational potential energy is at the top, that 98 joules, has actually now been converted into kinetic energy at the bottom, because in this particular instance, we're going to consider this a complete transfer. So since it's really close to the bottom, we know that there's no gravitational potential energy, because we'll call that as close to 0 as possible, or it would be so minimal that it wouldn't even be worth calculating. Plus, if we know that all of that energy was transferred according to the energy conservation rules, that means that that 98 joules of gravitational potential has now been converted into kinetic energy. So whatever you start with, 98 joules, is exactly what you end with, 98 joules. At the beginning, though, it was gravitational potential. At the end, it was kinetic. So that's an example of a complete transfer. Now, we could actually figure out some additional information about this object. For example, if they said, well, what is the velocity of the ball just before it hits the ground? And that seems maybe like a difficult thing to calculate, but we have everything we need. So if I want to find the velocity, I know that I'm going to be using the kinetic energy formula, 1/2 the mass times the velocity squared. Well, I know what the kinetic energy is at the bottom. We've already determined that that's 98 joules since we had a complete transfer. I know that the mass of the object is 5 kilograms, but I don't know the velocity of the object, so that's what I'm going to solve for. So if I do my 1/2 times my mass, I've got 98 joules. I've got 2.5 kilograms times velocity squared. So in order to isolate velocity, I'm just going to divide by 2.5 kilograms on both sides. So 98 divided by 2.5 kgs is 39.2. And remember, joules are kilograms times meters squared per second squared. So my kilograms are going to cancel, and I'm going to be left with meters squared per second squared equals velocity squared. But I'm not done. I don't have the velocity yet. I have the velocity squared. So we know if we have something squared, to get rid of that square to the opposite operation, we're going to take the square root. So I'm going to take the square root of both sides. So if I do square root of 39.2, I get some crazy number, 6.260990337. I'm just going to call it 6.3. So my velocity is 6.3. And then look, I took the square root of m squared, the square root of s squared, so I'm left with m/s. So the velocity in this particular scenario of this ball, 5 kilogram ball falling from 2 meters, the velocity is 6.3 meters per second just before it hits the ground. Okay, so I said in the beginning here, when we're using this equation, we are considering this a complete transfer of energy. All of the energy that we started with, gravitational potential and kinetic, gets transferred into all of the energy that we finish with, gravitational potential and kinetic. We know, though, that that is absolutely not true in the real world. So in the case of the ball, we started the ball at the top, and we dropped the ball to the bottom. If it was a complete transfer of energy, let's say this is a tennis ball. There we go, got a little tennis ball there. If I drop the ball from the top and I bounce it off the ground, if it's a complete transfer of energy, that means that the gravitational potential will all be converted into kinetic, which will then give it enough energy to bounce back up to the exact height that it started from. That's a horrifyingly bad tennis ball. We know, though, right now, if we grabbed a tennis ball and we dropped it to the ground, it is definitely not going to bounce directly back into our hand. It's going to bounce a little bit lower each and every time. Again, amazing tennis ball for your eyes. Every single time the object bounces off of the ground, it goes a little bit lower, a little bit lower, a little bit lower, eventually until it stops bouncing and hits the ground. So why is that happening? Well, why that's happening is we've got two situations that are actually affecting the total energy of the system, and we'll call the system just the ball. So when the ball drops, it experiences a little bit of friction and air resistance, and when the ball hits, you hear that sound, so we have a little bit of sound as well. That means that some of that energy is actually dissipated or released into the environment. And I like the word dissipated, because basically what that means is that energy is transferred maybe out of this system, but it's not gone. It's just been transferred into the surrounding environment. So a little bit of that, again, is friction or air resistance, so we would call that thermal energy. And then at the bounce, every single time it hits the ground, bounce, 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 you're going to have a little bit of sound energy. So while the ball will never reach the optimum height because of that dissipation of energy, the energy still is there in the form of thermal and sound. It's just now released into the environment, and it's no longer considered usable energy for the tennis ball. If this was usable energy for the tennis ball, if we could somehow corral this energy to stay within the ball, then every single time you drop the tennis ball, it would bounce back up to the exact same height, and it would literally do this forever. Now, that would be amazing, but that's just not how physics works. So sometimes we're going to look at a complete transfer of energy, for example, when you're actually solving some of the mathematical problems that you're asked to solve. But in the real world, we know that there's some dissipation of energy. And while the energy is conserved, it may not be conserved within the system. It may not be usable energy for whatever scenario you are experiencing or trying to calculate.